Hello everybody, today we'll be solving the two-sum problem. This is usually the first problem that most people solve when they're getting into their Leetcode journey. So let's get right into it. Given an array of integer nums and an integer target, return indices of the two numbers such that they add up to the target. So in the first part of the sentence, we're given the input, which is array of integers, and an integer target. In the second part, we're given the output, which is to return indices of what? Of the two numbers such that they add up to the target. Then you may assume that each input would have exactly one solution, and you may not use the same element twice. These are important assumptions that will help us solve the problem, and we'll refer back to them as we're solving. And you can finally return the answer in any order, which also helps us, makes it easy for us. So just going down, looking at the constraints, the first is the most important, which is the num's length will be greater than or equal to 2. So we don't have to worry about it being less than 2. And again, nums, they're all integers, target are all integers, and only one valid answer exists. Now looking at the examples, we have the input, we have the target, and the output is 0, 1. And the explanation that's given is 2 and 7, indices 0 and 1, which are 2 plus 7 is equal to 9. So this is what we're returning. Similarly, examples 2 and 3, indices 1 and 2, which are 2 plus 4, they add up to 6. Indices 0 and 1, 3 plus 3, it adds up to 6. So we return those indices. Now let's get into solving the problem. There are many ways to solve the two-sum problem. In the brute force approach, which we have already solved in another video, if you need more details on that, please check that video out. In the brute force approach, we have to sum each pair in the input array and check if it's equivalent to the target. So we will start with the 2, sum one by one with the rest of the elements, and see if the sum for each one is equivalent to the target. Then we'll do the same thing for the 3 and sum the rest of the elements and see if it's equivalent to the target. So we have to continually doing that till it's the end of the list. Although this is the most intuitive way of solving this problem, but it is also the most slowest. So the time complexity would be O of n squared, because we're comparing or summing every pair in the list and seeing if it's equal to the target. With the optimized approach, which we will be solving in this video, we will optimize the time complexity from O of n squared to O of n, which means we will only be looping through the list once, making the algorithm a lot faster. Let's jump into how we can solve it. The main thing we need to understand about the optimized approach is that we can take the target and subtract it with the numbers in the input array. And when we get the difference, if the difference is present in the input array, then we have found the one solution. For example, if you subtract a 9 with the first element in the list, 2, which equals to 7, if the 7 is present in the list, then 2 and 7 are the solution. But in this case, 7 is not present. And the reason for that is, if we add 2 on both sides, this cancels, equals to 9, equals 7 plus 2. So both the elements sum up to the target. Let's continue. Now we can subtract a 9 with 3, which equals 6. Again, 6 is not in the input array. Then we continue to 9 minus 4, which equals to 5. Is this present in the list? Yep, it is right here. So 5 and 4 are the solution. They both add up to 9. Now this algorithm is pretty inefficient because as we're looping through the list and subtracting the target from the numbers, we are also checking if the difference is present in the list. Checking if the difference is present, that is an O of n operation if we do that on the list. Because if we're checking for the 5, we have to compare the 5 with every element. Is 5 equal to 2, 5 equal to 3, 5, 4, and finally, we found the 5. Yes, it is present in the list. So we have to check every element in the list in order to find the element. To make this operation much faster, we can use the hash map. The time complexity of checking a number in a hash map is an O of 1 operation. The operation is O1 because we don't need to do a linear search through all the keys in a hash map. Instead, it uses a hash function to retrieve the exact index of the key for a specific value. Now there's two approaches we can use to solve this problem using the hash map. The first approach, we need to do a little bit of extra work. Initially, we need to loop through the entire list and load the hash map with the keys and the indices. So the keys will be all the values in the list, 2, 3, 4, 5, and their corresponding indices, 0, 1, 2, and 3. Once we have the hash map loaded, then we can loop again and subtract the target with the numbers. 9 minus 2 goes to 7. Does that exist in the hash map? And then check if it exists. Nope, it does not. We continue. 9 minus 3 equals 6. Doesn't exist. 9 minus 4 equals 5. We check if it exists. Yes, it does. So now we can return the index of the 4, which we're currently on, which is 2. And we can get the value from the hash map of the 5, which is 3. And we got our solution. Now, this takes the time complexity is first we loop through the list and load the hash map. This is of n. Then we are looping through the list again to subtract. This is another O of n. And then we are also checking in the hash map, which is O of 1. So overall, the time complexity is still O of n, which is a lot better than the brute force approach. The second approach eliminates the need for us to initially load up the hash map with all the input array numbers and their corresponding indices. So we will only have a single O of n operation. And the way we can do that is we would need to, as we're looping through the list, we need to first see if the numbers exist in the hash map. If they don't, then we need to subtract the target with the number and store the difference as the keys. So for example, check, does 2 exist in the hash map? Nope, right now there's nothing there. Now we can continue to subtract 9 minus 2, which equals to 7. And then we can store the 7 as the key, and the index will be 0, which is the value that we're subtracting. Then we move on to the 3. We see, does that exist in the hash map? It does not. Subtract a 9 with the 3, which equals 6. Store the 6 as a key, and the index of the 3 is 1. Move on to 4. Does 4 exist in the hash map? It does not. Subtract the 9, which equals to 5. Store the 5 and the corresponding index of 4, which is 2. Then we move on to the final element. Does the 5 exist in the hash map? Yes, it does. It does exist. So we have found a solution. So we can return the index that we're currently on, which is 3, and the index that we have stored, which is equivalent to the 5, we can retrieve the value and return that. And remember, the answer can be in any order. So this solution also works. Now let's see how we can code the most optimized solution. First, we're going to be looping through the entire list. And the code that I'll be writing here, it's very high level. It's not going to be syntactically correct, just for our understanding. we're going to be looping through the list. Is then equal to the length of the nums. Plus plus. And as we're looping, we're going to have our first condition to check if nums I is in our hash map. Right? If it's in the hash map, we will retrieve the key and return the values, right? We have found the solution. If it's not in the hash map, then we're just going to do our subtraction, which is target minus the nums I, and we will just store this difference into the hash map. Store this diff into the hash map, and the key will be the I. So this would be the diff, this would be the key, and the value will be the I, which we will store here. But if the key is found, nums I is found, then we can go ahead and return the I and the associated key in the hash map. Which would be this whole value. We will get the value for that key and return it. So let's walk through this a little bit. First, we're check, does the 2 exist? As we're looping, does the 2 exist in the hash map? It does not. We will go past this condition to the else. We will subtract the 9 minus 2, right? Which is 7. We will store this 7 here. And also the indices of the current element we're on, which is going to be 0. Again, we're going to loop to the next. This is I, now we're here. 9 minus 3 equals to 6. We're going to go to the else condition, store 6 here, and the I, which is 1. Then go to the next. 4 is 4 in the hash map. No, it's not. We'll hit the else condition. We'll do the difference, which is going to be 9 minus 4, going to be 5. Store the 5 here, and the corresponding indice of the 4, which is 2. Finally, we'll check again, does the 5 exist in the hash map? Yes, it does. The 5 does exist. So we're gonna hit this condition right here. We're gonna return the I, which is going to be I is going to be 3, and we're gonna fetch the value, this value from the hash map, which is going to be 2, and we will return this.